In this video, we're going to talk about logarithmic functions and equations. So let us write down a logarithmic equation. Log base A of B equals C. Now, it can mean one of two things. We'll just make one agreement. That A does look like the base. So either it's A to the B equals C, or it means A to the C equals B. Now, we're going to show that one of them makes no sense. If this is the same as, that's what the same as means, as A to the B equals C, A raised to the B equals C. Well, you know what? That's this. That means you could ignore the log. Well, if you could ignore the log, why are we studying logs? Okay, it can't mean this one. You can't just ignore the log and then get this. That means that you can always ignore the log, and why do we study about logs? So it doesn't mean this one. It means the one below it, which I'll put back in a moment. It means A to the C equals B. Now, again, as long as we agree that A is going to be the base, then it's not going to mean this. This log A base A of B equals C, log base A of B equaling C. It makes no sense at all for it to mean this, because that means just ignore the log. Okay, so I'm hoping that that's a way for you to remember that it means this. So, is this equation true? Now remember, this here is not 2 to the 3. It's log base B of 2. The log and the 3 are pretty much at the same level, and so is the 8. The 2's down there. There is no 2 to the 3. And I do have a little error. Okay. So the question is this statement true? Well, nobody's experts with logs. Nobody thinks logs. The question is 2 to the 3 equal 8? So either both those equations are correct or none of them are correct. Neither of them are correct. Well, 2 cubed equals 8. So yes. Yes. These two are. This equation is correct because that one's correct. If I ask you, is this equation right? You should verify that 3 to the 4th equals 81. Well, 3 to the 4th means this, which is 9 times 9. Yep, that's 81. So this is correct. How would you solve for x in this equation? Suppose that you were told that log base 3 of x plus 4 is equal to 5. Again, nobody knows how to solve this using logs. But we do know that's 3 to the 5th. 3 to the 5th must equal to x plus 4. Well, what is 3 to the 5th? 9 times 9, well, I know that's 81 times 3. So it's 81 times 3. Well, 3 times 80 is 240 plus 3 more. It's 243. So 243 is some number plus 4. Well, some number, when you add 4 to it, gets you 243. Well, this has to be 9, because 9 plus 4 is 13. Carry the 1. 1, that 1 plus 3 gives me the 4, and I'm going to have a 2 to get that 2. So x is 239. I mean, if you prefer, you can take away 4 from both sides. And that would be the answer to that problem. X is equal to 239. Let us look at the next statement that I'm going to say. I'm going to talk about notation. Whenever I write, or somebody writes log A, that shorthand log is shorthand notation for log base 10. If somebody writes ln of A, that means that ln is shorthand for log base E of A. E is a special number. E is approximately 1 plus 1 over n to the n for very large n. What on earth does that mean? That means that E is approximately 1 plus 1 over, put down a very, very large number, 1 over a large number, raise it to that large number, and you would have approximately E. If you say, well, that's not a good enough approximation, you know what? You're right. Make the numbers larger. Make these two numbers n larger. And what I have here would even be closer to E than when I didn't add on those 6 extra or additional zeros. The larger n is, now these n's are the same, but the larger they are, the closer you get to the number E. E is approximately 2.718. Just like the number pi, nobody can write it down because it's 3.141592665, and it goes on forever without repeating. This number goes on forever, and it doesn't the number E goes on forever, and it doesn't repeat. So I can't write down what E equals. But, I mean, more formally, I know you didn't. Oh, well, E is exactly the limit as n goes to infinity of 1 plus 1 over n to the n. In fact, that is the definition of E. 3 horizontal lines mean by definition. Like here, I can put that. Log of A, by definition, means log base 10 of A. ln of A, by definition, is log base E of A. E is exactly this limit. Now, let us go over some basic properties of log. Now, first of all, I should have said from the very beginning that A has to be positive. A cannot be negative. Because, for example, if you have log of negative 1/2 of x is equal to the cube root of 17.3, well, that would mean that x is equal to negative 1/2 raised to the cube root of 17.3. You can't raise a negative number to like the square root of 2 or, you know, less even, or the cube root of 17.3. Let us say just the square root of 2. This makes no sense. Because is this number positive or negative? See, if I raise it to an integer, and if it's an odd integer, I know it's going to be negative. And if it's an even integer, I know it's going to be positive. But if I raise it to an irrational number, I don't even know the sign, forget the number. A must be positive. Same thing over here. If A is negative, we just talked about this. If A is negative, what if C was the square root of 2? Is it positive, negative? Is it 0? I don't know. So A is understood to be positive. So what should this equal? Well, by definition, it means A to the box is 1. And you should know that A to the 0 is 1. As long as A is positive, A to the 0 is 1. In fact, even if A is negative, it's 1. It just isn't 0 to the 0, that's 1. But we don't have to worry about negatives because this number A is guaranteed to be positive. So it's 0 for any A. That is, if I ask you to solve this equation, log base 7 of 1 is equal to x, well, you should say, well, this means that 7 to the x equals 1. Well, that implies x is 0, because 7 to the 0 is 1. And only 7 raised only to the 0 power is 1. So we have this rule. What about this? What is log base A of A going to equal? Well, this means that A to the answer is going to equal to A. Well, A to the 1 is A. This is 1. Doesn't matter what A is. Log base 7 or 7, why, that's 1. Because 7 to the 1, which is 7, certainly equals 7. That is a second rule. Now, let us look at this rule. Log base A of A to the x. What is that equal? Well, A to this unknown value should equal to A to the x. Oh, I know this. A to the x equals A to the x. This is x. That is log base A of A to a power is just the power. Because, yep, A to the x equals A to the x. So if somebody asks you, what does this equal? You should say 5. Why? That's A, that's B, and that's C. 3 to the 5, yeah, it equals to 3 to the 5. Log base of 1/2 of 1/2 to the negative 2, this is equal to negative 2. Why? because 1/2 raised to this power does equal, it really does equal to this. I mean, something always equals itself. So we have yet another rule. These 3 rules were log base a of 1 is 0 for all a. Log base a of a is 1 for all a. And log base a of a to the x is x for all a. Those 3 are always true. So, again, if somebody asks you, what is log base 5 or 5 to the 4th? Don't say, oh, I need to go get my calculator, but even if I get it, I don't think it has a base 5 in it. A log base 5 button. Doesn't matter. Just think, and it's really not hard. 5 to what power? 5 to what power is the same as 5 to the 4th power? Well, I'm giving you the answer. It's 4. Oh, you mean it's that number? Yeah. It really is. Log base 3 of 3 to the x is equal to 7. Well, remember that equals x. That equals x. Oh, you mean x equals 7? You can't have this equaling 7 and that equaling x without x being 7. So that's one way of handling that problem. Another way is to take it a little bit slower and say 3 to the 7th is equal to 3 to the x. Well, you can't raise 3 to different powers and get equality. That means the 2 powers must be equal to one another. Let us look at a handful of problems. Suppose you have this one. And you get dizzy looking at it, like 3 to a power is going to give me 1 over 81. Well, just slow it down. 1 over 81, that's 3 to the 4th. But 1 over 3 to the 4th is 3 to the negative 4. Ooh, I know this one. It's negative 4. Because 3 to the negative 4 equals 3 to the negative 4. That is log base 3 of 3 to the negative 4 equals negative 4. Or, I should say, log base 3 of 1 over 81 is negative 4. And we can check it. 3 to the negative 4 should equal that number. Well, 3 to the negative 4, well, that's 1 over 3 to the 4, and 3 to the 4th. Oh, do not go like this. 3 times 3 is 9. I know that because I know up to my 12 table. 9 times 3 is 27. I know that. But 27 times 3 I don't know because I don't know my 27 table. Well, just think of it as 9 times 9. Oh, look at that. It is right. 3 to the negative 4 is 1 over 81. It really is. This is true. Okay, so yeah, 3 to our answer, that's our answer, does equal to 1 over 81. So, remember, I'm going to write down our last answer. Negative 4. That is, whenever you see this, it's negative 4. So what is 7 log 3 of 1 over 81? Remember, this is a number. So it's 7 times log base 3 of 1 over 81. So it's 7, it's this number times that number. This number is 7. That number is negative 4. The answer is negative 28. If I ask you, what is log base 3 of 1 over 81 plus 10? Well, you used to say, oh, that's negative 4. And if you didn't know what it is, first figure it out. Call it x. 3 to the x is 1 over 81, which is 1 over 3 to the 4th, which is 3 to the negative 4. Oh, x is negative 4 plus 10, 6. Let us look at the next problem. This is a doozy. Suppose you have log base 4 of the square root of 2. What does this equal? Well, let's call it x for a moment. So we know that 4 to the x is square root of 2. But you know what? I can write both the left side and the right side with a base 2. For example, the right side is 2 to the half. And 4 is 2 squared. But I have to raise that to the x. But here you multiply the powers. 2 times x is 2x. Again, I don't care if these powers are friendly looking, unfriendly looking. You can't raise 2 to different powers and get equality. That is, these powers have to be equal. What do you need 2 of to have half a dollar? The answer is a quarter. You have 2 quarters, then you have half. Say x is 1 quarter. So if I ask you what is this equal, you should say 1 quarter. And we can check 4 to the x, which is a quarter, should be the square root of 2. Well, 4 is 2 squared to the quarter. And that equals, or does it equal to the square root of 2? Well, we're supposed to multiply those exponents. 2 times a quarter is a half. And that does equal to the square root of 2. So here, x really is a quarter. I know, I checked it. What about log base 4 of 8 is equal to what? Now, there's a few ways of doing this. You can recognize that as 2 cubed. And you can recognize 4 as 2 squared. So this raised to that power should equal to this. That is 2 raised to the 2x should equal 2 to the 3. Oh, the bases are the same and we have equality. That means the exponents have to be the same. Say x is 3 halves. That was pushing it a little bit. If you have log base 4 of 8 equals x, well, this means 4 to the x equals 8. Well, the square root of 4 is 2, and if I cube that, I get 8. The x is 3 halves. That's another way of doing it. Here is one more way. This is probably how you might do this without using logs. 4 is 2 squared. So I want to think if this is different than what I just did. Okay, 4 is 2 squared, but I have to raise it to the x, and this is equal to 2 cubed. I look at those two numbers and I ask myself, can I write them using a common base? The answer is yes, 2. So 2 to the 2x is equal to 2 cubed. So the powers must be equal. Divide both sides by 2. You get x is 3 over 2. How about this one? How about log base 2 of x is equal to 3. So what is x? Well, this tells me, again, nobody can do these log problems. Nobody. In my opinion, not even the brightest person can look at this and say, oh, log base 2 of 8 is 3, without thinking exponentially. 2 to the 3 is x. Oh, I know what 2 cubed is. It's 8. So x is 8. Somebody may get this in a nanosecond, but they thought that. I can't imagine somebody knowing how to do logs in their head. Like, I can do 2 cubed in my head, but I can't do log base 2 of odd equals 3 in my head without thinking exponentially. I will think, oh, 2 cubed is 8, x is 8. And I can do that faster than the fraction of a second that I just said it. 2 cubed is equal to 8. I'll see 2 cubed so quickly, I'll go x is 8. It's faster than you can say your name. But, and that is true, I can do it quickly, in my head, no problem. But I have to think exponentially. Suppose you come to know that log base 5 of x is equal to 4. What's x? Well, 5 to the 4th is x. 5 to the 4th is x. But that means this. 25 times 25. How much money do you have if you have 25 quarters? Well, every time you have 4, you have $1. Well, 4 goes into 25 6 times with 1 quarter left over. You have 6 1/4. Log base x of 10 is 7. Well, this means that x to the 7 is equal to 10. Well, I don't want to know what x to the 7 is. I want to know what x is. So that motivates me to raise both sides to the 1/7 power for one reason. 7 times 1/7 is 1. And x to the 1 is x. So x is 10 to the 1/7, or you may want to write it as the 7th root of 10. I as a 1 is perfectly correct. X is equal to one of those two ways of writing it. Next, we're going to talk about graphs. Graphing logarithmic equations. If you want to graph x is equal to log base a of y, well, some people know how to graph log functions. I'm not one of them, or I have no interest in learning how to graph log functions, I would just write this exponentially. A to the x is equal to y. And I know how to graph exponential functions. Now this graph will either look like this, or it will look like this. It looks like the first one if a is bigger than 1, and it looks like the second one if a is less than 1 but positive. Remember, it makes no sense for a to be negative. And these graphs, they get closer and closer to the x-axis. The blue one gets closer and closer as x gets larger and larger, and the yellow one, let me try to draw it a little bit better, the yellow one gets closer and closer to the x-axis as x gets more and more negative. And in both cases, if x is 0, a to the 0 is 1, provided that a is not 0. And a is not 0 because it's either positive, or either because it's bigger than 1 or because it's bigger than 0. Either way, it's bigger than 0. So it turns out that you're always going to have the point 0, 1. Now, what if x is 1? So I claim that you can graph these functions with 2 points. Let the power be 0 and let the power be 1. If the power is 0, a to the 0 is 1. And if the power is 1, a to the 1 is a. Well, suppose that a is bigger than 1. So let's plot these 2 points. 0, 1 is right here. And when x is 1, a is larger than 1. It's up here. Perfect. The graph is like this. Just like I said, if a is bigger than 1. What if a is in between 0 and 1? Well, you still get the same 2 points. When x is 0, you go up 1. And when x is 1, you go up a. But this time, a is less than 1. Oh, you mean it goes like this? 2 points are enough to graph these exponential or log functions. Let us actually do one that's not as general as that one. Suppose you come to know that x is log base 3 of y. Again, there's no point that I can see. If you already know how to graph exponential functions, why on earth would you bother to learn how to graph logarithmic functions? But that's up to you. I know that 3 to the y, I meant to say x, 3 to the x is equal to y. That is, y equals 3 to the x. 2 points are enough to graph this curve. You let the exponent be 0 and 1, and that happens when x is 0 and 1. When x is 0 and x is 1. Well, y is 3 to the 0, that's 1, and 3 to the 1 is 3. Okay, so when x is 0, I go up 1. When x is 3, I go up 3. Sorry, when x is 1, I go up 3. 1, 2, 3, y and x, and here is my graph. Done. Next problem. X is equal to log 1/2 of y. Well, half to the x, half to the x is equal to y. Okay, so we plot 2 points, x, y. I let the power be 0, and I let the power be 1. That means x is 0 and y is 1. That will not always be true. When x is 0, a half to the 0 is 1. And when x is 1, half to the 1 is a half. Okay, so I graph those 2 points. And I say, boy, this is easy. When x is 0, I go up 1. When x is 1, I go up a half. And I say, there's my graph. Done. 2 points. Now, what if we make it a little bit more interesting? What if x is equal to log base 3 of y plus 2 minus 3? Let's bring this 3 over to the other side. You'll see why. Because now I can say 3 to this is equal to y plus 2. 3 to the x plus 3 is equal to y plus 2. How about we just bring the 2 over to the other side as minus 2. Minus 2. Now, all that changes in this problem is the vertex. Normally, that's like, that's the origin. Well, what's the new origin? What's the new vertex? Well, what makes that 0? That's the x value. And what that says, let me rephrase that. What makes that 0 is when x is negative 3. So for x, I put negative 3. And what that says, that's the y value. So the vertex is at negative 3, negative 2. It's as if this is the y-axis and this here is the x-axis. We're going to think of it that way. And we're going to ask ourselves the same question. We're going to have the x and the y. I'm going to ask the same question. And I'm going to look at this function right here. What makes this power equal to 0? And that's when x is negative 3. Well, 3 to the 0 is 1. Take away 2 is negative 1. Then, what makes this power equal to 1? And the answer is when x is negative 2. Negative 2 plus 3 is 1. So 3 to the 1 is 3, minus 2 is 1. Those are my 2 points. When x is negative 3, I go down 1. That's right there. And when x is negative 2, I guess that's negative 1 and that's negative 2. When x is negative 2, y is positive 1. And I draw my curve with 2 points and the vertex. Let us try a couple more like this. Suppose that x is equal to log base, or half, log base 1/2 of y plus 1 plus 3. Enough for 3's. Plus 2. So first, I'll bring the plus 2 over as minus 2. So this is log 1/2 of y plus 1. A half to that is equal to that. So 1/2 to the x minus 2, 1/2 to the x minus 2 is equal to y plus 1. Bring the 1 over. Okay. Y is equal to 1/2 to the x minus 2 minus 1. What is the vertex? Well, what makes that 0? I just want to look at something up here, please. Okay. What makes that 0 is when x is 2. 2 minus 2 is 0. And what that says is minus 1. So that's the new vertex. Okay? We still have to draw the xy axis, but we're going to pretend that at 2, -1, that's our axis. It's not our axis. That's what we're going to pretend that it is. Okay, this is our axis. And we play the same game as always. What makes the power 0? Find the y value. What makes the power 1? Find the y value. What makes that power 0 is when x is 2. So when x is 2, that power is 0. Half to the 0 is 1. Take away another 1, or take away 1, you get 0. What makes this power 1? Well, that's when x is 3. I mean, if you need to solve this and write it down, fine. When is x minus 2 1? You really should know that 3 minus 2 is 1. But if you add 2 to both sides, you'll discover that that happens when x is 3. When x is 3, the power is 1. Half to the 1 is a half minus 1. A half minus 1 is -1/2. I'm going to remove this side work. And I'm going to extend the x-axis. So, okay. 2, 0. X is 2, y is 0. That happens to be right here. 3, -1/2. Well, here's 3, and that's -1. So -1/2 is like right there. So we have that point. And I just come down like this, and I get closer and closer to my fake axes. All we did was take this graph. This is a graph of y is equal to 1/2 x, and we shifted it to the right 2 and down 1. We shifted it to the right 2 and down 1, right here. That's all we did. Okay. Let us do one more like this. So notice I'm able to do these with 2 points and without even knowing how to graph logarithmic functions. Log base 2 of our y minus 1 minus 2. Minus 2. So bring the 2 to the other side of the equation, and you get x plus 2 is log or something. which is good because now I can go write the exponential. 2 to that power, that whole power, 2 to that power is equal to y minus 1. Just bring the 1 over to the other side. And find the vertex. What makes this 0 is -2, and what that says is -1. So that's my vertex. Okay. So I draw my formal axes, and then I go to -2, -1. -1, -2, -1. I go right there and I pretend for the rest of the problem that my axis is really these two lines. Then I make my table x and y. What makes this power 0? -2. Again, if you want to work it out, work it out. X is -2. What makes the power 1? Well, it's going to be 1 more than that number. Take away 2, and you get that x is equal to -1. Okay, let me just erase my side work, please. Well, how much is the y value? Well, when x is -2, by design, that's 0. Well, 2 to the 0 is 1. Take away 1 is 0. And by design, when x is -1, this power is 1. Well, 2 to the 1 is 2, minus 1 is 1. We're done. We plot these 2 points and we draw a graph. When x is -2, the y value is 0. And when x is -1, which is right here, the y value is +1. The y value is right there. Okay, here's my graph. I plotted 2 points. There's my graph. Now, one thing you might want to do, and I've been looking for this. I don't think it happened in, oh, it did. Okay. We should find out where it crosses the x-axis, just to make our teacher happy. Well, we know that that's when x is 0. Okay, so we know that y is 2 to the x plus 2 minus 1. So when x is 0, we get 0 plus 2 is 2, minus 1, 4 minus 1 is 3. Okay, so it crosses at 3. And if we go back to the other ones, where did this one, where did that one cross? That is, what's the value right there? Well, we know x is 0, and this is our equation. So y is equal to 1/2. 0 minus 2 is -2 minus 1. But that's a half to the positive, that's 2 to their 2, or 2 over 1 to the 2. That's 2 squared, which is 4, minus 1 is 3. So once again, it happened to be 3. And I think the other one was below. Nope, it's above. So just make one minor change. Nothing major. I'm just going to make this go up higher. And I want to show that it does cross. Goes to the right forever and ever, so it has to cross. And here is our equation. Y is equal to 3 to the 3, because 0 plus 3 is 3, minus 2 is 27 minus 2, or 25. That's 25. So maybe we should use 3 points, 0, 25. We should use 3 points when it's more complicated than just y equals a to the x. Because I know where that crosses. If x is 0, you get y equals a to the 0, which is 1. I know it crosses at 1. In fact, it crosses one above the axes. One above. Well, look at this. Claiming it crosses one above. So oh. Yeah, you're going to have to do that. But if you notice, that was our new origin, and it did cross one above. It did cross the fake y-axis one above the origin. Okay. Now, these graphs that we've done were in the form of x equals log base a of y. Well, what if I interchange x and y? What if it's y equals? What if you have y is equal to log base a of x? Well, this means that a to the y is x. Well, if you think about it, so let me just write x first. X is equal to a to the y. When we had y equal a to the x, if a was less than 1, it went like this. And if it was bigger than 1, it went like this. Either case, it got closer and closer to the x-axis. But we just switched x and y. Okay? X and y just interchange roles. Instead of y, we have x. Equals is equal. A is a. X, oops, look at that, became y. So it makes sense that instead of getting closer and closer to the x-axis, now we're going to get closer and closer to the y-axis. Well, let's graph these. Suppose that you have that x is equal to 2 to the y. We're going to plot it with our same 2 points, x and y. I chose my words carefully. Find out when the power is 0. Oh, that's when y is 0. Find out when the power is 1. Oh, that's when y is 1. Well, what's x? Well, when y is 0, 2 to the 0 is 1. And when y is 1, 2 to the 1, which is 2, that's x. Okay, so 2 points. When x is 0, when x is 1, y is 0. That's right there. And when x is 2, I go up 1. And I have to get closer and closer this time to the y-axis. Oh, you mean it goes like that? Absolutely. That's how you graph this function. Well, actually, this is the same as log base 2 of x is equal to y. So I just graphed that one. Y is equal to log base 2 of x. what if I wanted to graph y is equal to log base 1/2 to the x? That number is less than 1, and of course that number was bigger than 1. Should you go and remember if this is bigger than 1, it graphs like this? Absolutely not. How on earth are you going to draw anything that looks like that and cross those 2 points? The answer is you can't. Now, this here is the same as 1/2 to the y is equal to x. Okay. Once again, 2 points. Let the power be 0. That means y must be 0. And let the power be 1. That's when y is 1. Well, when y is 0, you get 1/2 to the 0 is 1. So x is 1. Because x is equal to whatever that equals. When y is 1, you have 1/2 to the 1 over 1/2. So x is 1/2. With those 2 points, I can graph this. Just remember that this time we're getting closer and closer to the y-axis. Okay, so when x is 1, I go up 0. But when x is a little bit less, I go up 1. And I hope it's clear that to get closer and closer to the y-axis is going to go like that. Notice I don't even talk about, well, when the base is between 0 and 1, it goes one way. If the base is bigger than 1, it goes another way. No. If I have those 2 points and I have to get closer to the y-axis, it needs to go like this. It can't possibly come down and get closer to the y-axis. How on earth is this graph going across both of those points? If you have this point and this point, how can you be coming from down here? Okay, I mean, I guess in theory you can go up and then come down. But these graphs aren't doing that. It's just one quick movement. It's not go up and come down, just one quick movement. Okay, so what we do next, of course, is we put our famous fascias in them. We move the axes around. So how about we have y. Y is equal to log base 2 of x plus 1, or let's make it 4, minus 11. So we want to write this exponentially because I don't know how to graph log functions. Bring their 11 to the other side. And this becomes log base 2 of x plus 4. Well, put brackets around that. 2 to that, 2 to y plus 11 is equal to x plus 4. Bring the 4 over to the other side as minus 4. The vertex is going to be what makes the power 0, and that's the y value being negative 11. And what does that say? Negative 4. Where else you going to put the negative 4? I mean, you're not going to have two numbers by the y. So the vertex is at negative 4, negative 11. Y-axis, x-axis. X is negative 4. Y is negative 11. That's the point. That's the vertex. So we pretend as if that's the y-axis, and this here is the x-axis, and we play the same game like we always do. Let's find the 2 points. But now we want to find 3 points because somebody moved the origin and x can be 0. First, so this is our equation that we're going to look at. What makes that power 0? That's when y is a negative 11. I mean, after all, if y plus 11 is 0, you take away 11 to solve for y, you get y is equal to negative 11. And for the record, if we want the power to be 1, take away 11, take away 11, we get y is 1 take away 11, which is negative 10. So what are the corresponding x values? Well, when y is negative 11, this is 0. 2 to the 0 is 1, take away 4. 1 take away 4 is negative 3. When y is negative 10, that made the power 1. That's why we picked negative 10. 2 to the 1 is 2 minus 4. 2 minus 4 is negative 2. And for the record, if x is equal to 0, if x is equal to 0, well, if you subtract 2 quantities and you get 0, that's because the 2 quantities were equal to one another. Now 4 ended up being a good number because 4 is 2 squared. So you have 2 to this unknown power is equal to 2 squared. You can't raise 2 to different powers and get equality. That is, y plus 11 must equal 2. So y must be negative 9. Negative 9 plus 2 is, negative 9 plus 11 is 2. So y is negative 9. Keep our teacher happy by plotting their y-intercept. So I'm going to plot these points. Negative 3, negative 11, that's right here. And negative 2 minus 10, that's right here. And we're going to cross the y-axis right there at negative 9. So the graph goes like that, and there it is. You might want to find out where it crosses their x-axis. But those things depend upon your teacher, how exact he or she wants you to be. I'll do it one time. We know for sure y is 0 right there. We know that y is equal to 0. Okay, so we have that x is equal to 2 to the 0 plus 11 minus 4. So x is 2 to the 11s minus 4. And I just went through this. I think this is 1024. So multiply by another 2, get 2048. Take away 4. 2 to the 11 minus 4 is 2044. So at 2044, we cross the x-axis. So 2044. That's the x-axis. Let us do one more like this. Y is equal to log base, kind of base did we have last time? Log base 1/3 of x minus 2 plus 3. X minus 2 plus 3. First thing you should do is just get log on one side. That is, get rid of the 3, or get log of something on one side. So y minus 3 is log of x minus 2. So I had 1/3 to that power, 1/3 to that power is equal to x minus 2. Bring the 2 over to the other side, and we have x is equal to 1/3 to the y minus 3 plus 2. And we graph this exponential function. What is the vertex? Well, what makes that 0 is y equaling 3. And what that says, 2, that goes in the other slot. So that's the vertex, 2, 3. Okay, whatever. When x is 2, y is 3. So we're gonna make believe. That's what this is all about. Make believe. Make believe. We're gonna make believe that the blue lines are our axes. And we're going to find 2 points. When, what makes this, well, let me come here. What makes that power 0? When y is 3. And what makes this power 1? That's when y is 4. 4 minus 3 is 1. Well, what about when y is 3? That means that's 0. 1/3 to the 0 is 1, plus 2 more is 3. Now, if y is 4, then this is 1. 1/3 to the 1 is 1 plus 2. So you get 2 and 1/3. You want to write it as a mixed number? Fine. But it's a little bit more than 2. So now we're going to plot those 2 points. The first one, x is 3 and y is 3. Okay? X is 3, y is 3. The next one, x is, just to give myself some room, let us put 3 over here. So there's 3, 3. And maybe that point is 2 1/3, and I go up to 4. And we get closer and closer to the y-axis. So I just want to do one thing. Want to extend this. Now, since the blue y-axis is, well, let me graph it first. So it's going to look like this. Except I should hit that point. It's not going to cross the y-axis. That is, x equaling 0 makes no sense. We know that x is equal to 1/3 to a power. Now, regardless of what that power is, 1/3 to a power is always positive. And then when you add 2 more, it's going to be even more positive. That is, x can't be 0. If x is 0, we get this equation. We bring the 2 over to the other side as -2. And any base, any positive base to any exponent will never be negative. There is no solution. There is no y-intercept. Okay? What about the x-intercept? What about right there? Well, that's when y is 0. Okay? Maybe we'll have better luck with that. Let me do it here, please. We have x is equal to 1/3 y minus 3 plus 2. Well, if y is 0, we get 1/3 to the 0 minus 3, which is negative 3 plus 2. But that's 3 cubed plus 2. 3 cubed is 27 plus 2 is 29. So that's 29. And I would really think that you should somewhat have a scale. I don't think your teacher should take out a ruler and make sure that you live up to your scale exactly. Well, if that's 2, then maybe 29 should be over here. So, no big deal. I can still cross these 2 points, get closer and closer to the y-axis, and I'll cross at 29. Not a big issue. Okay, this is how you can graph logarithmic functions. By not graphing logarithmic functions, but graphing their equivalent exponential function. And graphing exponential functions, see, the thing is that I only have to know how to graph exponential functions. The alternative, and knowing how to graph exponential functions, I can graph exponential functions, and amazingly, I can also graph logarithmic functions. The alternative is to, maybe not for this video, but you definitely should know how to graph exponential functions, and you could learn how to graph logarithmic functions. But again, I've never seen a reason to learn how to graph logarithmic functions. That's something new that I have to learn. Why am I going to learn something new if something old that is graphing exponential functions I already know? Okay, I'm not into learning something new. And I'm sure I can learn it in a few minutes, but I have better things to do with my time. You don't need to learn how to graph logarithmic functions or logarithmic equations. Just know how to graph exponential equations. Am I saying you shouldn't learn how to graph logarithmic equations? Well, you're not going to learn it from this video, but that's your choice. Do you want to learn how to graph 2 different types of functions, logarithmic and exponentials? Fine. If you want to just learn how to graph exponentials and therefore know how to draw logarithmic, that's also fine. The third alternative is you can learn how to graph logarithmic equations, and if you're given an exponential equation, you can write it as a log. Now, the only problem I see with that is you learned how to graph exponential functions before you learned how to draw logarithmic. I assure you, if I was taught how to graph logarithmic functions first, like this one, and now I'm being asked to learn how to draw exponential functions, nonsense. I would convert the exponential function or equation, to a logarithmic equation. And like I said, I know how to draw logarithmic equations. So I wouldn't learn both, but that's your call. Good luck with this. Thank you.